Hi, this is Kevin. Welcome to my lecture on Chapter 1 of the Zelle 3rd edition Python programming book. And I'm going to assume, for the purposes of this lecture, that you've read the chapter. So let's get started. The objectives for the chapter I'm going to leave for you to read on your own. Okay, so the author really begins the chapter trying to establish what these computers are. So he defines a computer as a machine that stores and manipulates information under the control of a changeable program. So there are two parts. Computers are devices for manipulating information. We're not too surprised by that. Computers operate under the control of a changeable program. And by changeable, we mean changeable in the following sense, right? The computers that we use, which include a computer that could be on your desktop or a laptop or a tablet or your telephone or your smartwatch, these things run multiple programs at different time. We call them applications or apps. And at any given time, it's running one app or other. And the changeability has to do with the fact that we somehow tell the computer to run the app that we want, and we can change from app to app. That's what we mean by changeable. What's a computer program? Well, it's a detailed step-by-step set of instructions that tell a computer what to do. If we change the program, a computer performs a different set of actions or a different task. And this really works for both kind of meanings of the phrase change program. If we run a different program, then it's going to do different things. Or if we take the program that we have and we modify it, well, then the behavior is going to be slightly different than the last time we ran the program. So the machine stays the same, but the program changes. We say that programs are executed or carried out, and I often say that I run a program. Okay? Those all mean the same thing. And now the last claim here from the author is generally true, but I kind of want to modify it. He's saying all computers have the same power with suitable programming. For example, each computer can do the things any other computer can do. And this is generally true in a broad sense. For instance, it's pretty typical for us these days to have more than one computing device. And it's pretty typical for us to have some application that runs on more than one of them. You might have something like the Facebook app, or you might have a browser, and you might use them on a desktop computer, on your laptop, on your tablet, on your telephone, right? So all of these computers can run the same kind of apps. That's not to say that they have exactly the same amount of power, okay? Some computing devices have more memory than others, so they can run larger programs. Some computing devices run faster than others, so they can run the same programs but faster. But the fact is that these computers that run the devices that we're used to, they're all pretty much have the same kind of architecture. They've got, they're kind of packaged in different ways, and they can all run the same kinds of applications. Software rules the hardware. Okay, so by software we mean programs, and by hardware we mean the physical machine. The process of creating the software is called programming. More recently, a lot of people will use the term coding. It means the same thing. Now, why do we want to learn about this? Well, the author points out that it's a fundamental part of computer science. I want to point out in my class in the School of Information Sciences, we're not learning computer science, we're learning information science, and they're significantly different but related to each other. Having an understanding of programming helps one understand uh, the strengths and the limitations of computers. And this is going to be helpful for all of us in our lives because we use computers all the time. Sometimes we use them a significant amount in our professional life. Um, so these things can help us to become a more intelligent user of computers. It can be fun. I know it's a lot of fun for me. Um, it can be a form of expression, which is to say, programs can do expressive things. Like, for instance, well, there's a whole field of programming that uses programs to create visual art, and even sound art, light art, those kinds of things. So it certainly can be a form of expression. Here's a good one. It helps the development of problem solving skills, especially in analyzing complex systems, by reducing them to interactions between simpler systems. So there's a lot here, and let me unpack that a bit. So the initial programs that we're going to write are going to be simple. So we're going to be solving simple problems. But computer programs are able to solve complex problems. And how do we do that with computer programs? Well, we typically look at the complex problem and we break it up into parts. And then we might break some of those parts into subparts and some of those subparts into sub-subparts. Okay. And so we're going to be learning about how to solve problems in this way in this course. And it's a good way to understand problems regardless of whether you're going to write a computer program after you analyze the problem or not. And the last point from the author, programmers are in great demand. They certainly are. The programming jobs are good paying jobs today. They've been good paying jobs for 50 years. So that's a long time. And that should continue for some foreseeable time. Uh, so now we go on to talking about what is computer science. And I want to say again, in my class in the School of Information Sciences, we're not learning computer science per se, but this is interesting to talk about anyway. So he begins with a quote from the famous computer scientist Dijkstra, who said, computers are to computer science what telescopes are to astronomy. And that is to say that we're not studying computers, okay? We're studying how to solve problems with computers and observe those problems. And so a lot of computer scientists are interested in the question, uh, what processes can be described that can be done by a computer, and then what can be computed at all or computed feasibly. Some problems are still a little too intense to solve with computer programming. Um, Before we write a program, we design it. We have a strategy for how we're going to craft the code. Um, so if we're interested in what problems it can be solved, which is again what a lot of hardcore computer scientists would like to think their job is about. Uh, One way to show that it can be solved is to design a solution, okay, but that you could write a computer program for. And this is done by developing an algorithm. An algorithm is a step-by-step process for achieving a desired result. And the term that I use, that I think is more friendly to everyday people, is an algorithm is a recipe for solving a computing problem. Step by step instructions that lead us to the result that we would like to get. In cooking, when we use a recipe, it's usually a yummy result. Um, now, if in fact we're trying to figure out what problems can be solved by computer programs, the fact that we can solve one doesn't really mean that we can solve all of them. And that's maybe worrisome for the author because he really worries about stuff like this. I just want to point out that for us, kind of information practitioners, we're more typically trying to solve solvable problems. In a general class of problems, people like us solve all the time. And we may find one that's a little bit harder to solve than some, or a little bit easier to solve than others. But the fact is, we don't worry ourselves a whole lot about unsolvable computing problems in our information practice work. When you're going to design a solution, you often go through this thing called analysis, right? This kind of analysis that he wants to talk about is not systems analysis, but maybe mathematical analysis of mathematical problems. So he says analysis is the process of examining algorithms and problems mathematically. Um, some seemingly simple problems are not solvable by any algorithm. The problems are said to be unsolvable. And you can look these up. There are a whole bunch of things that are just too much mathematical work to solve the problem. Um, it, Problems can be intractable if they would take too long or take too much memory to be of practical value. And this is a good point because there are some problems that we can solve with the computing solution, but let's say that the cost of writing and running that program would be $100, and the value of solving the problem would be only $5. Well, it's solvable, but not in any kind of economically useful sense. Um, some problems that are hard to solve by kind of thinking them through, some kind of systems, for instance, that are um, kind of hard to analyze. Um, you can actually write software to simulate the system, and then you can study the behavior of the software. And there's a whole kind of field of computing where people are writing programs to simulate, oh, really kind of everyday things like how long do the lines get at the grocery store while you're waiting to check out, and when's the right time to open another cashier? Wow, you model that with software, and you do some experimental runs, and then you figure out if you open a cashier in certain circumstances, when you get a lot more throughput through the system. So there is a computing that gets done where we're trying to simulate things, and they simulate for things as tangible as that. They also simulate things like drug interactions with pathogens and things like that. Okay, now what do computers look like? Well, we know what the physical devices look like, but what we have here is a diagram of the kind of architecture of all the computers that we're used to using. Okay, so the main part of the computer is this box in the middle that has two parts: the CPU, the central processing unit, and the main memory, typically called random access memory, or RAM. And these two are very tightly connected with each other. And very interestingly, in the computers that we use, the main memory holds two things. It holds the program that we're running, and it also holds the data that we're processing. Maybe not all of the data, because we're reading that from input devices and storing some of it in the main memory. And then when we're done, we're writing it to output devices. We also sometimes store data and programs on this thing that in the diagram is called secondary memory, which are things like hard drives or solid state drives, SSDs, right? But one of the interesting things about these computers that we use, which if we were to characterize them, they would be called stored program general purpose computers, is that the memory, when things are executing, holds both our program and the data that we're currently accessing. Okay, and it's able to keep them from clobbering each other, which is from time to time challenging, but it usually works out. Okay, so this is the architecture. Input devices, things like the keyboard and the mouse. Output devices, it's thinking of things like the printer here, or your monitor, your screen. And secondary memory, things like hard drives and solid state drives, those kinds of things. Okay? Okay, so the CPU is the brain of the computer. It really it carries out all the basic operations. It does arithmetic. It'll test if values are equal. It also initiates the movement of data between it and main memory. Memory stores programs and data. Okay, and I talked about that. The CPU can only directly access information in the main memory, and typically that's RAM, or random access memory. Main memory is fast, but it's volatile. So when the program ends and when we turn the computer off, the contents of main memory are typically lost. Okay, and it's the secondary memory, things like the hard drive or the SSD drive or USB sticks and those kinds of things that store the data while the computer is off or when the program is not running. Input devices, again, keyboards, mice, etc. Output devices, monitors and printers. There's this thing, the fetch execute cycle. First, an instruction is retrieved from the memory. The CPU decodes the instruction to see what it represents. What it represents. It carries out the appropriate action. It fetches the next instruction. It decodes it. It executes it. Repeat, repeat, repeat. So the interesting thing here is that the kind of instructions that are executed on a computer by the CPU, they're very simple things, okay? And they happen very fast, and they happen in a repetitive kind of a way, okay? More to come on that. Now, what kind of language do we use to program computers? We don't use natural languages like English and French and Spanish and Mandarin and Hindi. Okay, we use programming languages because they're more precise and they squeeze out ambiguity. Now, ambiguity is in a lot of ways an advantage of natural languages because it helps us to describe things in a more artful way, I think. But it's a liability when you're trying to tell the computer what to do. Okay? So every structure in a programming language has a precise form called its syntax. So the rules of how you form the language, kind of character by character and word by word and symbol by symbol, are called the syntax rules of the language. And every structure in a programming language has a precise meaning, and those are the semantics of the language. Programming language is like a code for writing the instructions that the computer will follow. Programmers often call their programs code, and they call the programming coding. Now, there's not just one programming language, and there's not just one kind of level or style of programming languages. We have high-level programming languages and low-level. And the lowest level programming language is called machine language. And it really is made up with the instructions that that CPU on that computer knows how to execute. They're very small. They do very small things like load a value into register A, load a value into register B, add the value in register A to register B to give the result in register C. Unload the value from C back out to memory. Okay? It's very small increments of work. How can you get anything done? Well, computers are blindingly fast, and so they do very small kind of rote things, okay, but they do them very, very fast. So the language that describes that for any particular processor is called the machine language, okay, and that's as low level as a language goes. And high level languages are like the language that we're going to learn, Python. And they're more like English, and they look a little bit like algebra, and they're much closer to the human mental model of how to solve a problem than low-level languages are. So if we're going to program at a high-level language, but computers only know how to run a low-level language. Well, how do we bridge that gap? Um, oh, here's keep that thought. Here's the kind of work that is really done in machine languages. Load a number, add the two, store the result. Okay, very basic stuff. You're only going to get a lot of work done because the computer is blindingly fast. Okay, whereas a high-level language like Python kind of looks like this expression here: C equals sign A plus B. And this is kind of doing the same thing. We're adding two values that we have in the memory of the computer, and we're producing a third. Okay. And this kind of looks like a kind of algebra, okay, which is a lot of times what our mathematical computing looks like. And it's closer to kind of people's mental model of how to do math. So how do we translate from high level to low level languages? Well, we use these things called compilers. Okay, they're programs themselves. Well, who writes those kind of programs? Well, people who get degrees in computer science and go to work for companies like Apple or IBM or those kinds of companies, computer and system software companies. They write compilers, okay? And so they'll take a high-level language and compile it into a lower-level language, okay? And what would that look like if you wanted to see a kind of a system flowchart? That's what this is, of how this happens. Well, we begin with source code of a program, and let's say, for argument, that it's written in the C programming language. It's been around a long time. And then you run the compiler, and the compiler turns out machine code. And then you turn around and you load that machine code onto the computer again and say, run that machine code. And then you feed it inputs and it runs outputs. Okay? So that's, and again, who writes the compiler? Programmers who studied compiler writing in computer science courses at the university, who work for computer companies now. All right. Now, is compiling the only way to get from a high-level language to a low-level language? No. There's another approach called interpreting. So we have these things called interpreters, which are an alternative to compilers. And they read the source code, say the C language, or in our case, because Python is an interpreted language, let's say it's Python. And they simulate a computer that understands Python. And that's a bit of an exaggeration, but we'll let that go. So the source program is not translated into machine language all at once. An interpreter analyzes and executes the source code instruction by instruction. So one good thing about using a language that has an interpreted approach like Python does is it's possible to type little bits of Python into a Python interpreter, and it can run that little bit, not a whole program, whole coordinated program, but just a statement of Python or two. Okay, and it turns out that for learners, that's kind of a good thing. Okay, so here's the system flow chart for an interpreter. So we have the source code, the program. So that's a Python program that we wrote in our course. And then we might have some other input data that's going to run. And then we tell Python to run our program, and it interprets it and then runs the code um, as an interpreter. And when it's running our code, it translates inputs into outputs. Okay? And the only main benefit that we have, or one of the benefits that we get, is that we are able to type things into a Python command line, kind of a line at a time, and see what Python would do. Another benefit of interpreters is um, it's possible to set them up such that um, code is more portable from computer family to computer family, processor family to processor family. So interpreters are um, lead to more easily portable code. So, comparing, compiling, and interpreting, once a program is compiled, it can be executed over and over without the source code or the compiler. If it's interpreted, the source code and the interpreter are needed each time the program runs. That's true. Compiled programs generally run faster since the translation of the source code happens only once. Uh, and that's generally true. Um, Interpreted languages are part of a more flexible programming environment since they can be developed and run interactively. And that'll give us some advantages. Again, in fact, let me just kind of show you how that works. We'll probably see it in a slide or two, but I've brought over PyCharm here. And PyCharm is a tool that we're going to be using in my class. And let me close all the thing that I was going to show you later. But down at the bottom, there's a tab for Python console. And sometimes you see this and sometimes you can't see this line of tabs. If you can't see it, there's like a stack of squares in the lower left. And you can either click on the tab for Python console, or you can click on that stack of squares or hover over the stack of squares and choose Python console. And it starts up the Python interpreter, okay? And then we can begin to interact with it. So we might say something like, we have a variable called name, and we might assign it the string value Kevin Trainer, my name, and press enter. And you can see we got a prompt again. Okay. And then we might just type in the name of that variable, name, and press enter. And it shows us what the value is. So this is working up at the Python console. This is often called this this kind of style of interacting with a interpreter. It's called a read, evaluate, print loop, or REPL, all caps REPL, because every time we interact with it, it reads what we type, and then it evaluates it, and then if there's anything to print, it prints it. Now, this isn't the main way that we're going to program in the course, but it's great for learners, and you'll see examples in our text and other texts that have you working at the Python console, or REPL, if you would like to call it that. And that's one advantage in working in Python, because it's an interpreted language, and that's what we're talking about there. The other point that the author makes on the slide is that interpreted programs are more portable because of the fact that you only have to make one interpreter for each of the processor families that you're going to run Python programs on. So there's a way to explain that in more detail, and in fact, I probably will either in class or in another video recording, but that's all that we're going to say here. They're more portable. Okay. Let's go here. Oh, okay. So here we're starting up the interpreter, and you can see that when he wrote this text back in 2015, we were running a Python 3.5. And if I bring back what we saw a minute ago, we're already up to Python 3.10. So in 7 years, we've gone from Python 3.5 to Python 3.10. Most of what we learned in the course was already there in Python 3.5. I teach a couple of things that are later than that, and I will point them out. And so we've got some things here where we're saying that we want to print, and we're printing hello world, and you can see it prints hello world, and we can say print 2 plus 3, and it prints 5, and we say print a string 2 plus 3 equal, and then comma, and also the expression 2 plus 3, so then we get 2 plus 3 equal, that's string. We get a space every time we put a comma in between the things that we print using the print function. It adds a space, so that's how we get the space after the equal, and then we get the 5. So all of this was done at the console, not because that's how we're going to do most of our programming, but a lot of authors think that's a good way for you to learn. It's not something that I emphasize, but knowing how to do it will open you up to reading lots of Python books where authors like to send you down this path. More typically, when we're running, when we're trying to do something, we want to do a couple of things at once. And one of the things that we can do is we can take a couple of Python statements and we can collect them into this thing called a function. Okay, so how do I know this is a function? Well, it begins with a def. That's what we use to define a function. Then it has the function name. It has these empty parens, which later we'll see can hold something. And then we have a colon. The colon introduces the body of the function, which is made up of Python statements. So we, at the console, we typed in all three of these, and it didn't really print anything. And you would think, geez, if we ran that, we should print a hello, and we should print a computers are fun. But the fact is, when we define a function, we're saying, remember this function. We're not saying run this function. It's like the old game that we used to play, Simon Says. It's only when Simon says that you do a particular action that you're expected to do it. So we've never said to do hello. We've only said remember the parts of hello. Okay? So that's what we're saying here. Okay? But as soon as we type in hello paren, this is an invocation. This is a call to the function. which tells Python, remember that function hello? I want you to run it now. And so it ran it. Hello, computers are fun. Okay? So uh, defining a function and invoking the function are two separate things. Okay, what's the deal with the parens? Well, we haven't really been using them. They've been empty. But there is the possibility of having some text in the parens. In this case, we have this thing called a parameter name. So instead of hello, we've changed it to greet. Okay. Uh, and we have a parameter called person. Okay. And we're going to print the string hello and then a comma and then person. So are we going to print the word person? No, because these parameters are like variables. They take on a value. So we're actually going to print the name that we've been passed in person. So if we pass in Kevin, we'll print hello, Kevin, and then we'll print how are you. Notice that we don't run this. We never called it, so it doesn't actually execute yet. Okay, so now if we call greet and we pass the value Terry to be matched up with that formal parameter person, now it's going to run, it's going to say, hello, Terry, how are you? Isn't that pretty cool stuff? Or if we type in greet and then we pass in the value Paula, the string Paula, well then it's going to replace that person parameter name with the value Paula, and it's going to say, hello, Paula, how are you? Okay. The good things about these parameters is we can use them to customize the output of our function. Now, we've jumped in fast, okay? We're going to really learn about Python functions in chapter 6, okay? But we're trying to give you a feel for what can be done. So this passing parameters to functions gives you an idea of just one of the really important powers that we have in a language like Python. So what happens what happens to this Python interpreter when we're done? Well, in the real world, if we're using a tool like PyCharm that we're going to be using, we can just leave that console open and close PyCharm because we're done. Okay, but what if we wanted to leave the Python interpreter while there's a function called quit paren. If we did that, it just ends. Okay. And one of the things that I want to point out is that when we're running Python in this little Python console in PyCharm, what we're really doing is we're simulating what would have happened had we opened a command line window. So my computer is a Mac, and so when you open a command line window on the Mac, it's called a program called Terminal, but you can do the same thing on Windows. It's just a different program. And so if we wanted to run a Python interpreter from the command line, we would just type Python, enter. And there we are. We have started up the Python interpreter, and then we could say something like print hello, and it would print hello. I can't even spell hello. Or we could say name equals Kevin, and then we could put in the variable name, and it would echo back the value for Kevin. And then if we wanted to quit this and get back out into the command line, we could enter quit paren. And there we go. We're back out into the command line. So when we're using this Python console in PyCharm, if we want to close it, we can close it like that, right? And if we wanted to open a new one, well, we get the same one back. If we wanted to stop it, I guess we would want to stop it there. Okay, so no magic in PyCharm, just convenience. Okay. Somehow I advanced the slide when I wasn't quite ready for it. So I'm going to back up. So when we exit the Python prompt, the functions that we've defined cease to exist, right? All right. So if we're just typing things in at the Python prompt, they're not saved anywhere. Okay. So great for learning, bad for creating programs that are going to help us get our work done every day. So what we normally do is we put a bunch of instructions, a bunch of Python into a file. We often call that a module or a script. And it typically ends with a file extension .py or .py. Okay. And, when we when we create the file, we use a text editor. We can just open a text editor. And when we want to run a program, we start up the Python interpreter and we tell it to run the program. Okay. Now, this thing that we're using in PyCharm in my class is called an IDE. It's an integrated development environment. And when we want to use the console, well, then we do that. If we want to create a new program, well, there's a way to do that. We can click in the project and say we want a new Python file, and we might say it's my first test, and you don't put the .py on it, and you put enter, and it creates the file. Yours isn't going to be under version control like mine. And then we put the Python in. Okay. And then we save it. And then when we want to run, well, then we run it. And I'll show you the running of a program. Now, could we have done all this without an IDE, an integrated development environment like PyCharm? Yeah, we could have done it all out at the command line. It's just not convenient. So PyCharm and tools like it, these IDEs that programmers use, are for convenience and speed, and they're useful professional tools. Do we absolutely have to use them? No, we could get by without them. Okay. Now we're coming down to the end when we start talking about programs. So the first of the real full programs that would go into a program file is what we're showing here. He has a file called chaos, and he's shown us the code for it here on the top of the slide. And he kind of talks us through. So he puts the name of the program in a comment. These things that begin with a # space are comments. They're not executed. They're part of the documentation. So he has the name of the program and a sentence kind of explaining the intention of the program. He puts most of the code in a function called main, and that's the thing we're typically going to do. Right now, main is going to hold all of our code. We're going to be writing very small programs. Later on, like after we get to chapter 6, we're going to start to write larger, more complex programs, and they're going to be made up of more than one function. So, but the code that'll go into main then will be the main code, the coordinating and orchestrating code. So, and it will call other functions. So, in that context, the name main for this function makes sense. In the context of we're putting everything into main, well, it's a little obscure. So we do the parts of the program here. Remember when we use the def to define a function, we're not running it, we're just saying remember it. So the last thing that we need is a call to main where we say run main. Okay? So that's what's going on there. And when you run main, you get a bunch of numbers as output. Okay? Well, what's going on here? Well, he goes through this one part at a time. First, he explains the comments. Okay? Now, the first comment he has, it has the name of the file. This is sort of an instructor trick. Okay? In the real world, okay, when we're using tools like PyCharm, if you want to know the name of the file that you have open, you just look in the editor and you can see it. So this is kind of an instructor trick. So we won't be doing this in the programs that we write. He has a comment here that explains the intention of the program. A simple program illustrating chaotic behavior. That's a good practice. Okay. I'm going to show you in a minute or two. We're going to do it in a slightly different way. Okay. What's the next part? He defines the main. So this is the main function. Again, later on, if we get to chapter 6, we're going to have a lot of other functions. Main's going to make a lot more sense as a name. Right now, it's kind of a magical name for the only function that's going to be in our program. He prints up at the beginning of the program. This program illustrates a chaotic function. This is a pretty good practice. Generally, it's good for programs to print something in the output to show that they're started. And they might say something like this, or they might say, welcome to chaos. Okay. But it should be obvious to the user that the program has begun to run. So printing something at the beginning is a good thing to do. One of the things that he does is that his character strings are surrounded by double quotes. I'm going to show you in a minute or two that we're probably not going to do that. That's a little bit old-fashioned. Okay, you can use either the double quotes or apostrophes. Most modern Python programmers use apostrophes. Okay, he looks a little old-fashioned with this. The next line of the program it's got 3 things going on. Okay, at least 3. One is he's using this function called input to send a prompt out to the console and actually writes on the console, enter a number between 0 and 1. And then it waits for input to be typed. Okay. And then the result of that gets that into a function called eval, which turns that input into a number, okay? And then it stores that into the variable x. Now, ordinarily, I'm going to be claiming that single letter variable names are a very bad idea because it's hard to tell what they represent. But in terms of this, he's doing a math problem, and x is just the name of a variable. And, we're used to that from algebra, so we'll tolerate it. Okay? So he asks the user for a value for x, and then he has a counted loop, okay? And that's for I in range 10. That means it's going to run around 10 times, okay? We're going to have a lot more information on all the things we're learning in this chapter. So this is more a preview chapter than almost anything else. Then he's got an interesting thing. Inside the body of the loop, which is going to go around 10 times, he keeps recomputing the value of x. So it's 3.9 times the current value of x times 1 minus x. Okay, and then at the bottom of the loop, he prints the current value of x every time. Okay, and how does that look? Well, if we go back, you'll see that we go around 10 times, so there are 10 values for x. Now, it turns out that the nature of the formula that he uses is that it demonstrates chaotic behavior having to do with chaos theory. And it's a mathematical concept. And in chaotic behavior, small changes in input lead to large changes in output. Okay, and these values jump around a lot. Okay, and to a mathematician like Zelle, this is exciting. Okay, so in a very small program, we've been able to demonstrate the chaotic behavior of a mathematical function. Now, this doesn't excite me personally at all. Okay, I'm not really crazy about math. You may be, and you're in the right place. We're going to need you in this class to keep us all honest. But as the first thing I was going to have you write, or I was going to show you, I would have never shown you something like this, because this is pretty boring to me. Okay. Okay, so that's what happens. Okay, and let's catch up with where we were. Where we're going around 10 times. So yeah, we're going around the 10 times. And what he's really doing is he's showing you over on the right-hand side, going around a loop 10 times is kind of like just repeating this code 10 times. And it is, except that you don't have to code it 10 times. So that's the nature of a loop. Okay, so that's pretty interesting to see. This equal sign is called an assignment statement, and this looks like algebra, but it's not. Okay, but because here's what happens. Okay, when we come into a statement like this, all the variables like x have to already have a value. If we try to use them in order to compute a value and they're empty, the program's going to blow up and complain. It's going to say, we tried to use x and x doesn't have a current value. In our case, we already asked the user for a value, so it has one, right? So this is going to compute 3.9 times the current value of x times 1 minus x. Okay, and then it's going to take that value from this expression on the right-hand side, abbreviated RHS, and then it stores it into the variable x. So this isn't algebra. We're not saying that this is true at any one time. This says start by calculating a value using the current value of x. Okay, come up with a value for this right-hand side of the expression, and then the equal sign says, and then store the answer into x, giving a new value for x. Okay. The asterisk is assigned for multiplication. And just like algebra, if we need to group operations, we use parentheses to show how they're grouped. All right. And then at the very end, we call main, and it runs. Okay. And the author's super excited that this is chaotic. Again, your mileage may vary. Okay, and he's going into talking about why this is happening, and it's a logistic function. And I'm not excited about this. Now, if you're excited and you'd like to talk about it when we come to class, great, because perhaps you can inspire me. Okay? I don't want to denigrate people who are excited about math. It's just that not all of us are, and he's kind of lost me here. Okay? And so he's showing the difference between small changes in input. A 0.25 is input and a 0.26 is input. And we're getting completely different answers. Well, that's amazing to him. And good for him. Okay, so the math of this is less interesting to me than the programming of this. And one of the things that I'm going to do is I'm going to show each of the programs that he has. So this is the program that he has. I'm going to make the type a little bigger here. Okay, so this is the program exactly as it came, and at some point I give you a place where you're able to download the code, so you would be able to load this up too. But there's some things about the way he's formatted this and the choices he made that are not really what modern Python programmers do. Okay, the Python crowd, people highly interested in Python and highly capable are often called Pythonistas. Okay, and they talk about doing things the true Python way, which they'll say if you do something the true Python way, they say that it's Pythonic. And the problem is that these programs that appear in the book, they're perfectly good programs and they illustrate good learning points, but they're not as Pythonic as they should be. So what I've done is I've taken them and I've done this thing that we call refactoring. So what's refactoring? Well, first of all, let's take the program exactly as it is right here, and we right click in the editor window and we say we want to run it. Okay, and it asks us for the number between 0 and 1. Let's say 0.25. He did that. Okay. All right, and then we get the answer. So it runs just fine. We get a complaint. You'll notice down here that we have squiggly underline here. This is the code analysis part of PyCharm complaining. If we hover over it, it says that expected 2 blank lines after the function. Okay, and I don't know why we're not getting a complaint up here. We should really have 2 blank lines before it. So my complaints about the program as it appears in the book are, one, is it doesn't have enough blank lines. That's usually true because instructors are always afraid of running out of room on the slide. Okay, so they squeeze things together. Okay. The other thing is that the use of the double quotes are kind of old school and not modern. And the kind of comments we have up here are kind of old school and professorial as well. So what I did is I refactored the program. So what does that mean? Well, I didn't change the way it works. So if I take my new version, my refactored version, and I run it, okay, this one's called Chaos Refactored, and I put input of 0.25, well, I'm going to get the same output, so that works just fine. But I've kind of cleaned it up, okay? One is that I've got 2 blank lines after the function, so I'm not getting a warning. The other thing that I've got is the last thing in the file is an empty line that comes after the call to main. That would get a warning too. The strings are all what I call single quoted. They're quoted with apostrophes. That's more the modern kind of look. Okay. And then the other thing is I don't have a comment that says what the name of the program is. If you want to see that, you can just look up on this tab, okay? Why does an instructor add that? Well, he's printing it in the book. How can you know what file it's part of when it's in the book? Okay, so we're not going to do that. You and I are not writing a book. Okay, so we don't need a comment that has the name of the program. And so we do want a comment that kind of describes the intention of the program, but we're going to use a special kind of a comment called a docstring. And it looks even stranger than the one that's used by the author in the book, but it starts with triple quotes, 3 double quotes, full quotation marks, and it ends with 3 double quotes. Okay, and then we just have the same sentence, and you can do this. It's possible for these to be more than 1 line long. Okay, if they're nice and short, we usually just put it all on the same line. Okay, we not string it out over 3 lines. It would look like that. Okay. Okay, so we haven't changed a lot, but what we have looks more Pythonic. If we showed this to people in an interview, for instance, we'd look like we know Python instead of we just had a professorial Python course. Okay, and again, if we run this and we choose 0.25, we get the same answers. So what does it mean to refactor our code? Well, it means to change it to make it more readable, more testable, more maintainable over time without changing its function. And that's what we've done. And we're doing it right away. Okay? So, this is more the style that I'm expecting from you. I also want to point out that in the upper right-hand corner of the editor window, we have a green check mark. And that's what happens when we don't have any errors and we don't have any warnings. Okay, so for instance, if we got rid of the 2 lines after the function, we would get a squiggly underline here, and now it tells us we have 1 warning. And now we're going to cure that, and if we watch long enough, we should see our green check mark. All right, so I'm going to finish up here, and I'm going to say bye until next time. Bye-bye.